Okay, before going to the application of second law of thermodynamics, first we study or discuss the first statement of second law of thermodynamics. That is the Kelvin-Planck statement. Okay, we know that this is the impossible. What amount of heat we added, okay, we can't produce the 100% work. Okay, it is impossible for any device that operates on a cycle to receive heat from single reservoir and produce a net amount of work. Okay, I also going to discuss today the concept of reservoir. Okay, according to Kelvin, it is highly impossible to run any system in a single reservoir. What is meant by now reservoir? Okay, first we discuss the reservoir, then we move to the towards the applications. Okay, the word reservoir is very important for today's lecture. We can understood then and then we can understood the applications of second law of thermodynamics. The very important, it is the main core part of this chapter, the applications. They many times ask in exam what are the applications, what is the significance, like that. Okay, reservoir also is called as a thermal energy reservoir, TER. If we refer some books, they are also called as a TER, thermal energy reservoir. Is a large body, okay, a C definition, a large body of infinite heat capacity which is capable of absorbing or rejecting an unlimited quantity of heat without suffering appreciable change in its thermodynamic conditions. Thermal reservoirs are a large body. Okay, if I absorbing some amount of heat from that body, or I'm going to rejecting large amount of heat, or I'm going to absorbing large amount of heat. Okay, either we add or either we absorb from that body. Okay, there are no any appreciable change in its thermodynamic coordinates. There is no any appreciable change in its parameters, like its volume, like its temperature, like its mass, any thermodynamic coordinator. It doesn't affect. Either we absorb or either it's rejected from that body. Okay, there are many reservoirs. Anyone can know that reservoirs, natural reservoirs. Okay, if I take example of environment, if I take example of surrounding, okay, it is also one type of TER. It is one type of thermal energy reservoir. How? Suppose this is an exam system, this is a system, car system. Okay, and we know that the car is rejecting heat while in the form of combustible products, or during combustion via conduction via radiation, some amount of heat is losses to the surrounding, and we know that the heat is added in surrounding. Okay, okay, we feel that when I run the car or the bike in one day, full whole day, and we news heard on the TV because of some person is traveling their car and the environment temperature suddenly goes to the from 25 to 50 or 25 to 40. Okay, there is no any appreciable change in the temperature. So the surrounding is also one type of reservoir. Okay, one amount of heat add or one we absorbing heat from that air, there is no any appreciable change. So is the reservoir, is the natural reservoir. There is also one reservoir, that is the sea. Okay, sea is also one large form of reservoir, or this large body having infinite heat capacity. Okay, now hopes you understood the concept of reservoirs. Okay, natural reservoirs, that is the sea and surrounding of the sea and the air. These are some natural reservoirs having a large body of infinite heat capacity. These are the concepts of reservoir. Okay, in that any system, we have to run any system, we need two reservoir. Okay, and that reservoir is first is the source and another is the sink. Okay, that source, what mean by source and sink? in any system, any universe, if you take any example of any system in the universe, need two reservoirs. Okay, one reservoir is act as a source and another reservoir is act as a sink. Okay, when I'm going to apply this Kelvin-Planck statement, okay, according to Kelvin, it's highly impossible two system run under one reservoir. Means that according to Kelvin told that we need two reservoirs, source and sink. Okay, it's highly impossible to run the system within single reservoir. If you see this figure, okay, there is no heat loss. QR is a 0. But in practice, it's highly impossible. Okay, if you take the example of heat engine, if you assume the heat engine is a car, what amount of heat we supplied is directly can't get as a for to propel the vehicle. Some amount of heat is rejected to the environment here. Okay, so the Kelvin told that we need always two reservoir. Okay, when I take the applications, then you understood what is meant by now in depth, what is meant by Kelvin-Planck statement. In short, the conclusion of Kelvin-Planck statement, it's highly impossible. What amount of heat we supplied, it can't get converted into 100%. Or other statement, or in another angle, Kelvin told that it's highly impossible any system to run within single reservoir. This is the another statement or statement. We also discussed what is meant by Kelvin in yesterday's lecture. This is highly impossible. This is a possible because work is high grade energy. What amount of work is supplied is converted into the heat energy. And this is a possible because every system need two reservoirs. Okay, these two reservoirs. One is the source and one is the sink. This is the first application of Kelvin-Planck statement, that is the heat engine. The heat engine is the application of Kelvin-Planck statement. What is meant of heat engine? Heat engine nothing but every time heat engine means your IC engine. Wrong. Heat engine is the any system. See, the heat engine is any system where the heat energy is converted into work energy. That any system is called as a heat engine where heat energy is converted into the work energy. So if you take example of IC engine now, in case also we supplying heat energy, okay, in the form of fuel. Okay, that fuel is nothing but which form of energy? Mass of fuel into calorific value. Okay, going to burn with the help of some spark plug. So that heat energy is converted into the mechanical energy that propel the vehicle. So the IC engine is the also again best example of or the best application of Kelvin-Planck statement. We know that where what amount of energy is supplied from 100% and we get the propeller or the propeller speed is around 13%. The remaining is lost to the surrounding. So according to Kelvin, again, what is the source now? The source in that example for car engine, that is the mass of fuel, okay, and that is product of calorific value is the source. And what is the work output? That is the rotary power available at crankshaft. Okay, that is the work energy. And the main reservoir in that case, if you take there is a source, is the spark plug and the mixture of petrol and air is the source. And where is the sink? That sink is act as an environment now. The heat is rejected to the surrounding. What is the output? This is the rotary power. So it is the application of Kelvin-Planck statement which follows the Kelvin-Planck. According to Kelvin, it works because it needs two reservoir. One is the source, that is the surround mixture of petrol, air, and the spark plug. These are the act as the source. What is the sink? Environment is act as the sink. And what is the output? We get one rotary power. Okay, if I arrange is a like a block diagram, how it works? Okay, suppose it's a car engine. Okay, for car engine there is a two reservoir. You know that we need any system need two reservoir. Now we see which reservoirs act as a source and which reservoirs act as a sink. Okay, in car engine, okay, the car engine absorbs, car engine what absorbs? The source, from source, that is source is nothing but petrol plus air, okay, and that is car engine. What is the purpose of the car engine? We get work, okay, available at crankshaft, just simply, okay. Then if we see what amount of heat is rejected, what amount of heat is rejected to the environment, okay, we know that the heat rejection via that conduction, radiation, okay. So IC engine I write in the form of block diagram. So according to Kelvin, we need two reservoir. One is the source like petrol, air. We need the rejection of heat, which is heat is rejected in the another reservoir. That is the reservoir is act as a natural reservoir. That is the environment. Okay, in between that two reservoir, the system is works. So the car engine, or we call as a heat engine. Why called as a heat engine? Because the heat energy is converted into the mechanical work. So the car engine is called as a heat engine. Okay. So we see the another example of KelvinPlanck statement, that is the steam power plant or the thermal power plant. This is also best example. Thermal power plant. This is the same working figure I also discussed in the steady flow equation. The same main components of what is the boiler, steam turbine, condenser. Okay, you know that the functioning now where the boiler, what is the boiler now? We generate steam. Okay, in the boiler, what is the source for the boiler? That is the combustion of fuel plus air. This is the source. Okay, now that source is that supplying heat to the water, the heat is generating steam, and that generated steam is going to impinging on a turbine and we get work. And some amount of heat after expansion, or some amount of heat or steam after expansion, that low pressure, low temperature steam is going to reject by that condenser, and that rejected heat we cool in condenser. So that again low pressure, low temperature steam is converted into water, and the same cycle is going to repeat. Now how sir it is applicable for Kelvin-Planck statement? This is a question you arises in your mind. Okay, how this is the best application? Okay, now I am going to discuss with the help of some block diagram now. Okay, for boiler generate steam. Okay, but while generating, before generating steam, we need to add some heat. Okay, so I am going to add heat here. It's like a furnace, such as a furnace. So furnace in steam power plant is act as a source. Okay, any system there is a two reservoirs. One reservoir is a source and another reservoir is a sink. So one reservoir is act as a source. In case of boiler is a furnace. Assume that furnace is a continuously burning. Okay, it's going to continuously going to burn. Is a constant large infinite heat capacity. I assume that the furnace is continuously burn at constant temperature. So I assume that the furnace is also one type of reservoir and which is a source for steam power plant. Okay, then generating steam is going to impinge on the turbine and we get work output. We get work output. Okay, after getting work, some amount of heat is rejected, or that low pressure, low temperature steam is going to the condenser. What is the role of condenser? We are going to removing the heat from steam. We are going to removing heat from steam. That is a function of condenser. Okay, so that steam is again cool and that converted into again water. That steam is converted into condensate. Okay, and then cycle is completed. So heat is rejected now to the environment now. How environment? Because suppose the condenser is like a closed vessel and there is one piping like that, and I am going to circulate cold water in contact with that high pressure, low pressure, low temperature steam, the steam temperature rises more than that cold water. So steam giving their heat to that circulating cold water, and that cold water become now hot water, and that heat is I'm going to reject in environment. Like that heat is now rejected. So in case of that heat engine, on the heat engine, why it is called as steam power plant heat engine? Because we supplying heat energy and we get work done from the turbine. So heat energy is converted into the mechanical energy. So steam power plant is also another best example of Kelvin-Planck statement. Any heat engine is the best example for Kelvin statement. So if we see here in the form of block diagram now, okay, here is the boiler, this is the turbine, this is the condenser, and this is the pump. And that whole circle, actually whole circle is nothing but this system. Okay, for that boiler we supplying heat, added heat, okay, from source, and source is act as a furnace, and that from condenser we rejecting heat to the environment. So environment is act as a sink, and from that turbine we get work done. That circle is nothing but that indicates the whole system. Okay, I draw here. If you see, the circle is nothing but the whole system is act as that circle, heat engine. So if you see the heat engine, the source is the furnace and the sink is the environment. Okay, now what about the temperature? Okay, there are two reservoirs. I always told the two reservoir 1, reservoir 2. In that reservoir, one reservoir is always high temperature and another reservoir is always low temperature. But is nothing means that always high temperature reservoir is always source, is never. Okay, change according to application. Okay, just you remember there are two reservoirs, or one reservoir is high temperature, another reservoir is a low temperature, and in that two temperature any system always runs. It's highly impossible to run system within a single reservoir. We need always two reservoirs. Okay. Okay, now we see the how to calculate some performance of that heat engine. Okay, I am taking example of, suppose there is a from furnace we get 100 megajoule of energy. Okay, the work is produced around 55 megajoule. So what is my rejecting heat is nothing but, okay, I expect always I supply 100 and I can get 100, but practically not possible. I can get 55 amount of energy. Now what amount of rejection heat is 45. So what is the formula of work developed? I want what amount of heat we added, but we can't get practically. Some amount of heat is rejected. So it is the work done. And so the performance of the heat engine measured in the form of thermal efficiency. We call as a word thermal efficiency. Performance measured in the form of thermal efficiency. I write here the thermal efficiency. So what is the formula, fundamental formula of any efficiency? Sir, it is the output upon input. So what is the main role of any heat engine? I am told that heat engine, it is a work producing device. I can get the propeller, rotary shaft, rotary power like the car. I can get rotary power in the form of turbine. So what is the output? Is nothing but the work developed. Okay, and what is the input? What amount of heat supplied? So what amount of work developed here? So it is nothing but QA minus QR amount of work is produced. And what amount of heat we supplied? Okay, what amount of heat we add? That is the QA. Okay, and use the notification QA and QR. So it is the thermal efficiency. In the form of temperature, I write also thermal efficiency. The QA is correlated with the furnace temperature. So it is a higher temperature. And the QR is correlated with the lower temperature. That is the sink temperature. That is the lower temperature T2. And the what amount of heat added from that furnace at higher temperature. So it is the T1. So the thermal efficiency I can write also T1 1 minus T2 upon T1. This is the thermal efficiency. We can write in the form of temperature. Write down this formula is very important. or in the form of heat or in the form of temperature. These two formulas are very important. Okay, so heat engine, I am going to conclude. Heat engine is the application of Kelvin-Planck statement. According to Kelvin-Planck statement, we need two reservoirs. One is the high temperature reservoir, another is the low temperature reservoir. In case of steam power plant, high temperature reservoirs act as a furnace, low temperature reservoirs act as a sink, and its performance measured in the form of thermal efficiency, and the formula is 1 minus T2 upon T1. Hopes you understood the Kelvin-Planck statement and its application. Write down this formula.